Life and business are defined by decisions. We make lots of decisions every day. We decide what to wear, how to get to work, or in the time of COVID, if we're going to be leaving our house to go to work. Computers can help analyze potential outcomes of decision alternatives. And spreadsheets are one such computer-based tool to evaluate decision alternatives. And they are the foundation of what we will evaluate and discover within this decision analytics and management science class. So in business analytics, generally speaking, we have had some big wins. Chevron was able to develop an optimization tool for operational and strategic planning, mixing crude oils and planning capital expenditures for an annual savings of $1 billion. And while this may not be healthcare, operational and strategic planning, mixing chemicals, and planning capital expenditures are all very much healthcare related issues. Dell built analytics models to optimize hardware configurations, its web design, and promotion design and timing. And again, in healthcare, we have web design, we have promotion design and timing, and we have to develop hardware, whether it's IT hardware or the physical plant of a hospital. And the benefits were found to be over $142 million. This stuff sounds pretty good, right? Kroger also found enormous benefits from using business analytics, including this spreadsheet modeling and linear analytics. In this case, they were focusing on their pharmacy and were able to reduce prescription stockouts by $1.6 million, making many happy customers. They lowered inventory by over $120 million and increased revenue by $80 million. 3 huge wins for Kroger's pharmacy operations. The National Broadcast Network Company in Australia is the government-owned broadband provider in Australia, and they used these tools to optimize design of network, servicing 8 million locations, which reduced network design time and saved them over $1.7 billion while reaching more and more remote parts of Australia. Another great healthcare application is the Alliance for Paired Donations, where transplant patients needing a kidney often have potential donors who are incompatible. The Alliance for Paired Donations finds exchanges with other patient-donor pairs to optimize paired matches. And since 2006 through about 2014, the Alliance for Paired Donations has saved about 220 lives, which is absolutely outstanding. So computer models represent a set of mathematical relationships and logical assumptions that we implement in a computer as a representation of a real-world object or phenomenon. So we can do this using spreadsheets like Excel, but there are also more complex software like R that can be used to create models. Spreadsheets are especially convenient, however, because for simple to moderately complex computer models, users generally have more familiarity with these tools like Excel. So everybody uses models to make decisions in some manner or another. There are 4 primary types of models. There are mental models. So when you're moving into a new house or apartment, you might look at an empty room and visualize internally how you might organize that furniture. That's a mental model. Visual models represent things like blueprints and roadmaps are less common. You may see in many buildings maps to help guide you in the event there's an emergency or a fire. That is a visual model that tells you how to safely escape from a building that is literally burning down. You can also have physical or scale models, which are common in aerodynamics. Buildings may also be considered physical or scale models. When I was a kid growing up in Vancouver, British Columbia, we had the Pacific National Exhibition every August. And in one of the rooms, they had a scale model of the entire province of British Columbia. And you could press different buttons to illuminate railroad tracks, roads, different types of facilities. And it was my favorite thing about the PNE, or the Pacific National Exhibition. But right now, we're working with mathematical or scale models. So, as an homage to our visual mall models, you are here, and that star is exactly where we are, and that's where we are coming from. Models are usually simplified versions of the things that they represent. Valid models accurately represent the key characteristics of the object or decision under study. It's important to point out, however, that models don't need to be a complete representation of what you're interested in investigating. The model just needs to represent enough that it is able to produce valid output. So we can think for a moment about how we might model improvements to an assembly line or a vehicle intersection. And I challenge you to take just 2 or 3 minutes to think about how you might make those changes. Or how might you make changes to the flow of a hospital pharmacy, an in-house hospital pharmacy. Models can help us do a lot of things. So there are some enormous benefits to modeling. First is the economy, is that it's often less costly to analyze decision problems using models. For example, if we're looking at an in-house hospital pharmacy, it's probably easier to use software like AnyLogic or Arena to sketch out different structures to deliver medications throughout the hospital, rather than to spend weeks trying different methodologies and potentially confusing your staff. Models also often deliver needed information more quickly than their real-world counterparts. And finally, feasibility. Models can be used to do things that would otherwise be impossible to do. And sometimes they help us discover what is impossible to do. So this is an example of a mathematical model. And all 3 of these expressions express how a mathematical model works. And I want to show it to you like this, because I want you to know that for as funky and mathematical as some of these models may end up looking, you can work your way backwards to words. So we could say that profit is an expression of revenue minus expenses. So that is the simplest way that we can explain what profit is. It's revenue minus expenses. But many models are expressed in terms of functions. So our profit would be a function of revenue and expenses. Now, when we're working theoretically, we don't typically use words like revenue and expenses, and instead we'll assign letters. Same thing with our dependent variable profit. So ultimately, when we're expressing something mathematically, our profit or dependent variable would be expressed as y, and our independent variables expressed as x1 and x2. But know that all three of these expressions are the same, and if you're trying to populate that y is a function of x1 and x2 and it's not making sense, work backwards and use words. If you can read and use words, I promise that you can get yourself through this class and these problems. So here the generic mathematical model for these types of problems is y, or the dependent variable, is equal to a function defined by the independent variables, which are inputs having impacts on y. So revenue, expenses, but you can have an infinite number of x independent variables, although I don't recommend it. So most spreadsheet models are very similar to our generic mathematical model, except you might find them a little bit easier because we're using words. Most spreadsheets have input cells representing our independent variables, to which mathematical functions, so our f, are applied to compute a bottom line performance measure, which is that dependent variable, or y. And there are three types of analytical models. And right at this point, we are focusing on prescriptive models, where the form of the function is known and well defined. We know our independent variables, or they're under the decision maker's control. And we have some analytic techniques, including linear programming, multiple optimal linear programming, nonlinear programming, and so forth. Up to this point in the statistics classes and other analytical classes you've taken, you've had experience with predictive and descriptive models. So when we're looking at solving problems for leveraging business opportunities, this is the general structure of that model. The first thing we need to do is identify our problem. So one example of that could be that you have an inefficient system for delivering medications throughout a medical facility. So you can formulate and implement your model. You'll analyze your model using spreadsheet tools, test your results. If you don't like your results, no harm, no foul. Go back to formulate and implement your model and repeat that cycle until you find a solution that you find to be satisfactory. Models can be used for structurable aspects of decision problems, but other aspects can't be structured easily, and they require intuition and judgment. However, human judgment and intuition are not always rational, so it is very important to make sure that everything you do is in the best interest of your model. So one psychological effect that is encountered in these types of spreadsheet models and decision analytics are anchoring effects, where some trivial factor that was picked up early on in the process is hung on to tightly as the process proceeds. And one example of this is that when the Model T was produced, you could only get it in black. And this anchoring effect was maintained even as other automakers were producing cars in other colors. It was believed that the color was so irrelevant that it didn't matter, that it only came in black. And in the meantime, Ford has never caught up to its rivals, and it's been a pretty long time for them not to have caught up to their rivals based on that one anchoring effect. Framing effects refer to how decision makers view a problem from a win-loss perspective, and the way a problem is framed often influences the choices in irrational ways. So let's consider A scenario. And I say a scenario as opposed to multiple scenarios because these scenarios are actually the same. So suppose you've been given $1,000 and must choose between receiving 500 more immediately or to flip a coin and receive 1,000 more if heads occurs or $0 more if tails occurs. Now suppose you've been given $2,000 and must choose between giving $500 back immediately and flipping a coin and giving back 0 if heads occurs or giving back 1,000 if tails occurs. Note that these two scenarios are the same scenario, but they're phrased differently. Think about it. Is there one that you would prefer over the other based on how it's framed and phrased? And here we can even see, using a decision tree, what our different alternatives are in a decision tree. And we can see that, generally speaking, our payoff is going to be about $1,500. From the initial state, if it's heads, we may end up with $2,000 or tails $1,000. But it's the same regardless of which scenario you find yourself in. It's also important to note that good decisions do not always lead to good outcomes. A structured modeling approach to decision making helps us make good decisions, but can't guarantee good outcomes. So I like to look at this table just to think about the outcome quality versus the decision quality. Sometimes the decision quality is good and the outcome quality is good, so there is deserved success. Other times the decision quality is good, but the outcome quality is bad. For example, if you started a restaurant business right before COVID started, your decision quality might have been good, but the outcome bad because 2 months later COVID started. In other situations, your decision quality can be terrible and you still may end up lucky. Dumb luck. A lot of people who go into the entertainment industry seem to liken that to their success. Although sometimes you can have bad outcome quality and bad decision quality, and that's just what we would call poetic justice. Good decisions harmonize what we can do, what we know, and what we want, and to which we are committed. And I can't think of an industry where this is more important than in healthcare. Up next, we're going to investigate optimization and linear programming.